All right, welcome back, Hononegah Honors, Algebra 2, 8.1, starting a new chapter now, defining and using sequences and series. Now, a sequence is an ordered list of numbers, so a pattern, if you want to say. Now, there are some very specific sequences, such as arithmetic sequence and geometric sequence that we will be doing this chapter, but it's here in section 8.1, we're just talking about a general sequence. Now, a finite sequence, basically there's a limited number of terms, meaning there's an end. That dot, dot, dot that you see in the domain and range, but there's an ending value there. So the values of the range are called the terms of the sequence. Now, it is important to note the notation here. So the first term of the sequence is a sub 1, or the second term of the sequence is a sub 2, and the third term of the sequence is a sub 3. So there's a little notational situation there that we're talking about that we got to make sure to understand. So if I have a pattern of numbers, the first number in the sequence is a sub 1. Now, an infinite sequence is a function that contains without stopping. So again, dot, 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 forever. So notice this one here is an infinite sequence and it never ends. So the next number would be 10, the next number would be 12, and dot, 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 it goes on forever. So a finite sequence, as we just talked about, has an ending. So notice 8 is the last number. Now, and this is going to be a little bit more challenging, a sequence can't be specified by an equation, meaning there's a rule to this particular sequence. Both sequences above can be described by this notation. That's the way we're going to probably read it. A sub n is equal to 2n, meaning the first number in the sequence, I put a 1 in for n. The second number in the sequence, I put a 2 in for n. The third number in the sequence, I put a 3 in for n. And notice when I put that in, I get the number that is that particular value in the sequence. Now, the domain of a sequence can begin with 0 instead of 1. The domain of a finite sequence is then the set 0, 1, 2, 3, dot, dot, n. And the domain, the infinite sequence, becomes the set of non-negative numbers. Unless otherwise indicated, though, we will begin all of our sequences with 1. So write the first 6 terms. So I want to know if I put 1 in for n. So the first number in the sequence is 1. If I put 1 in for n, what do I get? Well, I get negative 2.5, or I'll just put it as a decimal, negative 2.5. If I put 2 in for n, I get negative 2. If I put 3 in for n, I get negative 1.5. Okay? And this would be a dot, dot, dot. Okay, but those are the next 3. This is actually a arithmetic sequence. Again, we'll be talking more about that later, but you're putting 1 in for n, 2 in for n, 3 in for n, and so on. Next one, what happens if I put 1 in for n? I get 1. What happens when I get 2 in for n? I get 2. 3 in for n, I get 4. Okay. If I put 4 in for n, I'd get 8. So again, this could be a dot, dot, dot situation. This is actually a geometric sequence. And we'll talk more about it as the semester or the chapter goes along. Writing the rule. Now this is probably the hardest part about today. When the terms of the sequence have a recognizable pattern, you may be able to write a rule for the nth term. There is no formula in today's lesson. You are basically writing a rule given the information that you have. And this rule has to work for all the terms in the sequence. So notice the first one here. 1, 3 halves, 2, 5 halves. So I want to describe the pattern, write the next term, and then write a rule. And so again, this is the hardest part of today. So what is the next number in the sequence? Well, the next number in the sequence is going to be 3. And what's happening each time? They're adding a half. So each time they're adding a half. So what would the rule be? A sub n would equal. Now, this is, again, where it gets a little bit tricky, is we got to come up with, so the first term is 1, the second term is 1.5, the third term, and so on. So we have to come up with something that will work for each one of those. What if I did a half n plus a half? So the first term, if I put a 1 in, I'd get 1. The second term, if I put a 2 in, I'd get 1.5, or 1/2, 3 halves. If I put a 3 in, I would get 2, and so on. So again, you are writing a rule in which the first number, the second number, the third number, the fourth number, and so on will work in this case. So now the next one, 4, 8, 16, 32. So this one's a little more challenging. It's not just adding the same number each time, but I noticed that 4 is 2 squared and 8 is 2 cubed. So this is 2 squared and 2 cubed and 2 to the fourth and 2 to the fifth. So I see a pattern there. So now what can I do? The next number then would be 64 in this particular pattern. Describe what's happening. Well, they're raising the exponent. They're multiplying by 2 each time. So what if I did 2 raised to the n plus 1? So the first term had a 2 to the second, and the second term had a 2 to the third, and the third term had a 2 to the fourth. So this would be a rule that would fit all the numbers in the sequence. All right, now I get a pattern here, and again, there's no necessarily equation or formula that I can use to get this, but here we go. First one, they added 3, and the second one they added 3, and the next one they added 5, and the next one they added 7. So the next one, if they add 9, would be 24. So, sorry for the pause there. Another way of looking at this is the second term is 3, the third term is 8, the fourth term is 15. I also notice a little bit about the fact that's 1 less than something squared, like the first term squared minus 1, or the second term squared minus 1, or the third term squared minus 1. So in other words, each time it's taking whatever n is, it's squaring it and subtracting 1. And so the rule that we could write, instead of the addition rule, is we could write something dealing with squares. And that is a common practice in this particular section, is dealing with the fact that what happens if I square the number. So again, this one is going to be very challenging for you. So it's the square of the term minus 1. In the video game, you start with 12 points and earn 2 more points for each minute that your avatar is active. Write a rule for the number of points in each minute the avatar stays active. Then graph the sequence. So you start off with 12. And then the next minute you have 14 points. And the next minute you have 16 points. And the next minute you have 18 points. So you're going to earn points each minute that you're in. So you start off with 12 and add 2 more each time. So the rule, now this particular sequence, let's start with 0. So if I have 0, I get 12. If I have 1, I have 14. In 2 minutes, I have 16. In 3 minutes, I have 18. So we're going to start with our domain being 0 for this particular situation. Because again, you start with 0 minutes, you have 12 points. So that can be a little bit misleading. You could also then do 2n plus 10. Right? That would also work, but then your domain would start with 1. So this is if you start off with a sub 0. Now, graph the sequence. So I'm going to graph this. And again, because I started off with 0, I'm going to use the top one here. So, and I'm going to use some color. So 1, 2, 3, 4, 5, 6. And I know I'm not going to go that far. 12. So then the next minute I have 14, and the next minute I have 16. Notice that there's a gap. I'm not connecting my dots here because this is actually considered discrete. These are individual points. It's not like if I go half a minute, I end up with 1 point. It's every minute it goes up 2 points. So again, if I don't make it to the end of that minute, I don't get a partial. So this is considered a discrete, not a continuous graph, because again, it's not connected. So now, when the terms of a sequence are added together, okay, so if I add them up, this is considered a series. Instead of a sequence are individual numbers. So when talking about a series, you're talking about the addition of each of the terms. So instead of a comma in between each one, you're actually going to have a plus sign between each one. You can use summation notation to write the series. For the example, the two series above can be written in summation notation as followed. Now, let's talk a little bit about this summation notation. It looks like a giant E. It's the Greek letter sigma, and that indicates addition of. Now, you'll notice I don't like the use of i's. I usually use n when doing those, but so when you're looking at this notation right here with the big E, it's saying I'm going to put 1 in for I, and that is the first term of the sequence. And because it's, the series then, and so then I put 2 in for I, and I get the second term of the series. I put 3 in for I, and so notice it has a beginning and an ending. So 1 is the first one, and 4 is the last one. So if I'm asking you to do a summation, I'm just going to ask you to add each one of these. So 4, 6, and 8. And so the answer to this question when I add it all up is 20. Now, this is a different notation, and it won't be in this particular chapter or this particular section, but notice that goes from 1 to infinity. So dot, dot, dot. And a lot of times there is no sum to an infinite series, because it keeps going, and the next number that you add to it would make it bigger, and the next number you'd add to it make it bigger. But there are some situations that you will be able to add up an infinite series, and we'll talk more about that later. For both series, the index summation I and the lower limit of the summation is 1. The upper limit of the summation is 4, and infinity for the infinite series. The summation notation is also a Greek letter, and I said this earlier, but it's the Greek letter sigma written as an E. So write each series using summation notation. So again, the first, I'm going to use n again. So the first term is 1. Now, I have to figure out the rule, and then I have to figure out what the last term would be. So let's say it goes from -1 to 2, 2 to -3. So it's going up by 1, but each time it's changing signs. Okay, so the first term of the sequence is -1 times n, and this -1 is to the nth power. Think about that now. -1 to the first power would be -1, times 1 would be -1. -1 to the second power now is positive times 2. Anytime that you are seeing the numbers flip back and forth from positive to negative, you're raising it to the nth power. Now, so the last number in the sequence would be 40. So there's 40 numbers in this particular sequence. So then the next one, we're starting off with 1, and this one's going to infinity. Notice the dot, dot, dot at the end. So now I have to actually write the rule. The first term is 3. The second term is 9. The third, so this is 3 to the first, 3 to the second, 3 to the third. So we're talking about 3 raised to the nth power. So again, writing the rule for the summation notation. And then the last one, it's got a dot, dot, dot at the end. So we're talking about infinity. Notice there's a 1 on top every single time, and then the bottom, let's say it's 1, and this is 2 squared and 3 squared and 4 squared. So it's basically taking the 1 over n raised to the nth power. Let's see if that works. If I have the second term, it's 2 squared, third term, so it's not, sorry, not to the nth power. I made a mistake there. It's just squared. Apologize for that. So again, infinity means it goes on forever, and it's 1 over the n being squared. Actually find the summation notation. So they want you to put 3 in for k. So if I put 3 in for k, I get 11. 4 in for k. So this goes up each time all the way till you get to n. So 4 in for k, I get 15. 5 in for n, I get 19. 6 in for n, I get 23, 7 in for n, 27, 8 in for n, 31, 9 in for n, 35. And then I'm going to get out a calculator and I'm going to add those up. So remember, summation notation is adding. So I'm going to take 11 plus 15 plus 19 plus 23 plus 27 plus 31 and plus 35. Sorry, a little calculator mess up there. I believe this is 161. Special ones. If you are in math club or you're involved in some of these competition type things, these are the ones that usually show up. Is anytime you're doing the sum of terms of one. Now that one's a little bit easy, but basically it's saying if I add up a bunch of ones. So if I had 1 plus 1 plus 1 plus 1, there's 4 ones, so the answer is 4. So that one's a little bit easy. That one usually doesn't show up, but this one definitely does. The sum of the first n positive integers. So basically they want to know what is 1 plus 2 plus 3 plus 4 plus dot, 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 40 kind of thing. And they could go on to whatever number of numbers that they want. This is the formula that will actually give you the sum of all the numbers 1 through 40 or 1 through 100. So instead of sitting there adding up 1 plus 2 plus 3 plus 4 plus 5 plus dot, 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 all the way to 100, then you could just plug 100 into that formula for n, and it would work. The next one, also a formula. So the sum of the squares of the first positive integers. So basically, if I had 1 squared plus 2 squared plus 3 squared plus dot, dot, dot squared, this is another formula that you can use to find the sum depending on how many numbers they're asking you to do. So again, math club, I won't ask you to memorize either one of those. But if you are a math club person or somebody that's interested in doing something like that, please make sure to write that down. You may want to program your calculator with that particular one. So let's do one of those. As part of an experiment, a teacher gives 1 paperclip to the first student and 2 paperclips to the second student and 3 to the third and 4 to the third until they go up to 25 students. So using that formula from the previous page, it's right here, the n, parentheses n plus 1 divided by 2. So n plus 1 divided by 2. How many paper clips did the teacher give out? So 25 plus 1 divided by 2. So 25 times 26 divided by 2. And I believe the answer is 325 paper clips. Homework assignment is out of the book. If you have any questions, please make sure you talk to your teacher, and good luck.